Hello, welcome back. So in this lecture, we will cover chapter 18 about time complexity and big O. So the chapter outline, we will cover the following topics. First, we will go over the definition about time complexity, the big O. And then we will take a look at how to do time complexity analysis. And then we are going to compare the orders of the magnitude and then compare about the various search algorithm and also sorting algorithm. And lastly, we will also discuss the approach for time complexity regarding recurrence relationship. So the first question is, what is the time complexity and is a big O? Okay. So generally speaking, it's to determine which algorithm is better. If you recall, last chapter, we discussed various sorting algorithm. Okay. So with the same size for the data set when we do the sorting. So which algorithm will be faster? Is it or in some other cases is what what about the metric used to assess the memory to run those algorithms? But in this chapter, we mainly discuss about time complexity for the, so it's also called big O, okay? And so generally speaking, so about algorithm determine better, you can like either analyze from time perspective. So then it's to evaluate the execution time. Okay. So then in this case, we call it time complexity. Or you try to assess the memory used to run the algorithm. Then that's regarding the space complexity. So generally speaking, when we determine algorithm better, then we consider whether either the execution time or memory usage. So it depends on the situation. But in this chapter, we are going to discuss regarding time. So the time complexity, how we measure, we use a concept, we call it a big O. Okay, so what is a big O? So the definition of the big O, okay. So it says generally the performance metrics represented the big O notation. Big O notation is O, and within it we have a function Fn, okay, and n is the data size. So n is the input data size to run that algorithm, okay. So it's some function f regarding the data size. So n is data size, input data size to run the algorithm. Okay, so some function, okay, and we represent as O and then Fn, okay. So how do we come up this function Fn? So it's derived from a Tn. So Tn is what? Is to measure the time required to execution of algorithm for n elements. Okay, so basically, this is a total time for the execution of the algorithm, considering like the input data size is n. Okay, and normally when we try to derive this Tn, what we do is we count the total number of statements going to be executed by the algorithm in in your either like the coding, okay, or the algorithm. So you count. So here is a key term, the total number of statements executed. So that's the key part. So total number of statements, we do the count. So if you have the code for the algorithm, then we can do the count, okay? So when analyzing the time complexity, and also generally, okay, it's not just one for all cases. Generally, there are three cases. Normally, we consider, okay, we consider the best case scenario, average case scenario, and worst case scenario. Okay, so what are those? When we discuss example, we will have a better understanding about these three cases. So generally, speaking about the three cases, is best case is to perform minimum number of steps on the input data. And normally, this is not very informative. Okay. Later on, we will see, like for the previous chapters, bubble sort, is it? So for the bubble sort, if the data already sorted in ascending order, and if we want to sort them also in ascending order, then that's the best case. That's the best case. Okay. So average case is as performed an average number of steps. But normally it's also difficult to determine. Okay, that's difficult to determine. So in the scenario of like the bubble sort, so maybe the data just randomly ordered. Okay, so it's not the best case, not sorted, not not also in the other case is the completely reverse order. Okay, it's just randomly ordered. Then that's considered as average case. So worst case is going to perform maximum number of steps. And usually we use it as the benchmark for calculating that Tn, if you recall, okay, that Tn. And Tn then derive Fn, okay. And how do we find the Tn is to count total number of statements executed when we run the algorithm. Okay, so that's Tn. So worst case is maximum number. So normally that's used as a benchmark. Okay, and in the bubble sort scenario, if the input data is in reverse order of like either in descending order, if you want to sort it in ascending order, then that's at that time. So that's a worst case scenario. Okay, then next, let's see. So our goal is to find this Fn for the algorithm. And normally it's for a category of algorithm. It's not for each specific uh, some cases, running cases. No, it's just a general. Okay. And so the Tn is to count the total number of statements executed. So what's the relationship between these two so that we can come up the general time complexity is it for a certain algorithm. So the idea is that the algorithm is said to be, and we also call this, so when we we read it order Fn. Okay, so this read as order Fn. So the idea is if it can be expressed as order Fn, then it says if there exists a positive constant C. Okay, so because this is a positive constant C, so that for all sufficiently large n, so anyway, for the input n, but sufficiently large n, okay, the time to execute the algorithm meet the following relationship, okay? So, uh, what's the definition is? So if you can find a constant, positive, okay, and the times that function Fn, and for sufficiently large n, okay, and you can guarantee that is always larger or equal than that Tn, okay, or we can move the Fn as it to the left side of this relationship, then it is Tn over Fn is less or equal than C. Okay. So if you can find a positive such constant and times that function Fn and make this relationship be true, especially when n is large enough, then we say, okay, Tn is order Fn. Okay, so that's how we find this Fn, derive this Fn and the relationship between Tn and Fn. Okay, and the common example for function Fn, normally we have n. So n, so order n. So that means it's a linear relationship. Okay. And n quadratic. So this order n quadratic. So this is quadratic relationship or log 2n Fn. So log relationship or n times log 2n or 2 to the n and also 1. Okay, so if you write as this 1, then this is constant. So constant, so the time complexity is constant. That means your algorithm doesn't depend on the input data size. It has nothing to do with n. Okay, so then it's constant. And a good example for constant is if you recall in previous chapter, when we learn the data structure stack, if you recall. And for stack, whenever you want to add an item at the top of the stack, so that has nothing to do with the data size. So that operation is an order, so it's a constant. Okay, so it's order Fn is 1. So it's an order 1 relationship. Okay, big O. So basically, it is a constant. Okay, and so we understand the concept. Is it so? Our goal is always to find the Fn, and Fn derived from Tn. Okay, so in this section, we are going to discuss how we derive Fn. So we call it analysis of time complexity. Okay. So here is an example. It's just a part of the code. Okay, so code snippet that's related to read n elements into an array. Okay, so we have an integer I, set it to 0. Then we have this while loop, and the loop based the times based on this n. Okay. And then you do input that number to the array. And then you increment that I. So because this I control the number of times of loop. So when this algorithm is running, then you can clearly see that this first statement will be just run once. Okay. And then how many times this while loop statement will be wrong. Then because it starts 0 all the way to n, including n. So that's why it's going to be executed n plus 1 times. Okay. And then within the loop, so this scan, so this input statement, it will be executed n time because when I is n, it's not included in the loop. Okay, so that's why it's n times. And same thing, this I increment will be executed n time. So then we can sum of that the times. So we can see we have 3n and then plus 2. So that's how we come up with Tn is 3n plus 2. Okay. And 3n, so if you recall previously, we said the goal is to find a constant. So our goal is to find the Fn. So we need to find a constant. So over here, when n, especially when n is large enough, is it? So then we can see, we can always guarantee. So if we choose C is 6 and Fn is n, so that's linear, if you recall in the previous slides, is it? And then we can always guarantee this is true. Is it? When n is greater or equal than 1, then it's always true. Okay, this case. Because it's always true, then we say, okay, Fn is n. Okay, Fn is. So what this represents, just represent, okay, to read n elements into an array, this algorithm is a linear algorithm. So this code snippet shows a linear algorithm. Okay, so it is n and it's order n. Okay, so what this means, it means linear relationship. That means if n doubles, then Tn also doubles. So the time to run, when the data size doubles, then the time to run it will also be a double. So that's the time complexity. Okay, the big O. Okay, next let's take a look another algorithm. Okay, so this time this algorithm has nested loop. Okay, so let's take a look. So the outer loop from 0 to n. So it will be n plus times. Okay, no problem. Then for inner loop, so the inner loop j itself will be n plus 1 times. Okay, but it will be wrong how many times? Because it's within the outer loop, is it? So basically, when I is 0, then J loop will loop n plus 1 time, is it? When I is 1, it will also loop n plus 1 time. When I is 2, it will also be n plus 1 time. And until I is n minus 1, it will loop n plus 1 time. Is it? So totally how many? So it's based on the outer loop number of times. Is it? So n times. So that's why this loop itself will be n times n plus 1 time. Okay. And then suppose we are going to do something here. So how many times? We know outer loop is n time and the inner loop is not going to include n. So j runs all the way to n minus 1. So that's why it's n times n, okay, because this is from j and this is from I, okay. And after we analyze each statement total times that it will be executed, and then we can sum of them. So sum of them. So it will be, so we have 2n squared. Okay, we have 2n squared. How many n we have? We have 2n. And how many constant? We have 1. Is it? So this is our, basically this is our Tn. Is it? So we come up with Tn. So our goal is to find a constant that times that Fn. Okay, so Fn, so basically this is a polynomial. Generally, if your Tn is a polynomial, normally we pick the highest order term as the Fn. So highest order term is n squared. That's it. So we choose the n squared as the term for Fn. Okay. So in the case of polynomial, choose the highest order term. In this case, it's n squared, so we pick this. So now the question is, how do we find the constant? Is it to guarantee when n is greater or equal than 1, that the equation will always be true? Is it? So here it says, okay, if you try c is 6, then it will work. So this relationship will always be true. Of course, you can choose C is 7, C is 8, C is 9. Okay, some other positive concept will also be fine. Okay, so this C will make this relationship always true. Okay, so we say, okay, we find the constant C, and then we can say, okay, the Fn is n squared. Okay, and Fn is n squared, so then the Tn, so the time complexity, the big O in this case is n squared. So then, because Fn is n squared, so then we know this relation is not linear like the previous example shows, is it? So this relationship is a quadratic relationship. And what does this mean? That means when n doubles, is it? Then the time running that will be roughly grow by a factor of 4. Okay. If n triples, then the time to run it compare with when the size is n, then will grow by a factor of 9. So it always follows the n square trend. Okay, so it's quadratic. So clearly you can see the time to run in this case is that this is going to be longer than than linear. Okay. Okay, we already discussed the two examples, how to derive the Fn for the big O for the time complexity. So generally speaking, okay, what is the order of the magnitude? So what are the commonly used function for Fn? Is it, and also keep that in mind. N is regarding the input data set size. Okay, so common values is like order 1. Okay, order 1, so keep this in mind, let's represent a constant. And order n square, order log 2n, order n times log 2n, and order 2 to the n. Okay. So let's see. Order n is constant time. So constant time, then like we previously explained, no matter what the size is 10,000 or 2,000 or 20,000 or even a million, and it's always the time always be the same. Okay, no difference. So that's constant time. Order n, so this is linear growth. Linear growth, as we previously explained, so it takes twice as long when data size doubles. Okay, so here gives an example. When n is 10,000, so if your algorithm runs when n is 20,000, then the time, it will take twice the time. Okay, so that's linear growth. And then we have n squared, so quadratic growth. The quadratic will take 4 times when data size doubles for the execution time. Okay, so if data size 10,000 and it grows to 20,000, then the running execution time will grow 4 times. So we can clearly see if you compare quadratic and linear, definitely a quadratic will take longer as if for the same data size. And the next is log 2n. Log 2n, it grows, so it's called log growth. It grows slowly, okay? So when n increases to the next power of 2, is it? Then log 2 will only increase by 1. So it's quite slow. So here give an example. When n is 8, log 2n is 3. When it grows to, so 8 is 2 to the 3, and 16 is 2 to the 4. Is it so? When it grows to the next power of 2, but you see log 2n only increase by 1. So it grows very slowly, okay? And we can see the log 2n even grows slower, much slower than linear. So it's pretty idea if you have some algorithm that can run log 2n. It grows very slowly, okay? And then 2 to the n. Uh, so 2 to the n is the power grows. Okay, so this grows very quickly because when n increase by 1, then the execution time will doubles. So here give an example is that when n is 5, so 2 to the 5, it will be 32. But when n is 6, that so increase only by 1, but 2 to the n is 64, it's already doubles. So grows quite quickly. Normally, we don't want our algorithm to run like this, okay? Okay, and this is a table for the magnitude comparison for common big O Fn function. Okay, and here we have the input data size n. Okay, and this is the constant. You can see it doesn't change. Okay, no matter the data size, and n so quadratic. And then you can see from 2 grow to 32, it grows quite a lot, okay? And then next is n times log 2n. If you compare these two, you can see n times log 2n grows slower than n squared, okay? And 2 to the n, you can clearly see it grows so fast that even just from 2 to 32, it already grows from 4 to over 4 trillion. And if you took a log 2, then we will see it grows really slowly. So from this comparison table, we can clearly see that if our algorithm the time complexity is log 2n, that's pretty good. If the algorithm is design an algorithm that runs the time complex at 2 to the n, then that's a bad algorithm. Okay. Okay, and previous slides is about it's use a table to compare the different magnitude of the Fn. Okay, so here we have the visual, so the curve for different Fn. Okay, and this the bottom case. This is for log 2n. You can see it grows very slowly, okay? And then the next one, this one is a linear, okay? So you can see log 2n is even slower than linear. And what next one is n log 2n, okay? So definitely n log 2n, then it grows faster than linear, okay? And then we have quadratic, but we can also see, compare with n log 2n and n square, then definitely it's better than n square, okay? And the worst case, you can see it's a power, okay? It grows too fast, okay? So from this visual comparison, we can also see that a preferable algorithm is going to be like this lower part, okay, not this one. Okay, so let's take a break. Um, so this is one of the national parks, and let's see. And so here are the two photos. So can you guess what the national park it is? Yeah, so we will review it at the end of this chapter. So that's about this lecture. We will come back in a little bit. Thank you.